For the last 25 years, we had a story about how the universe ends. A clean, cold, inevitable story backed by Nobel Prize-winning science, confirmed by hundreds of independent observations, and woven into the very foundation of modern cosmology. The universe, we said, is expanding. Not just expanding, but accelerating. Galaxies racing away from each other faster and faster, driven by a mysterious invisible force that fills all of space. That force has a name: dark energy. And according to everything we understood, it was constant, unwavering, eternal, a fixed property of the universe itself, like a permanent thumb pressed against the cosmic scale, ensuring that expansion would never slow down, that stars would fade, that galaxies would drift beyond each other's sight, and that the universe would end not with a bang, but with an infinite frozen silence. We called it the Big Freeze. We taught it in textbooks. We built cosmological models on top of it. And then, in 2025, more than 900 scientists, using the largest three-dimensional map of the universe ever constructed, looked at the data, looked at each other, and said, something is wrong. Dark energy is weakening. And if it continues, everything we thought we knew about the fate of everything is on the table. To understand why this is so deeply unsettling, you need to understand what dark energy actually is. Or rather, what we don't know about it. That's the more honest version. Dark energy is a term scientists use to describe whatever is causing the universe's expansion to accelerate. That's it. It is a label for our ignorance. We know it exists because the evidence for it is overwhelming. In 1998, two separate teams of astronomers observing bright, exploding stars called Type Ia supernovae noticed that the most distant ones were dimmer than expected, implying they had moved away from Earth faster than anticipated. The universe wasn't just expanding, it was speeding up. The discovery was so revolutionary, so entirely unexpected, that it won the Nobel Prize in Physics in 2011. But the nature of this force, what it actually is, where it comes from, why it has the strength it does, none of that has ever been explained. Despite the fact that dark energy represents roughly 70% of the total energy in the cosmos, it remains, in the words of physicists who study it daily, completely mysterious. The simplest assumption, the one that worked beautifully for decades, was that dark energy was a cosmological constant, a fixed, unchanging energy density built into the fabric of space-time itself. Einstein actually introduced this concept over a century ago, abandoned it, and called it his greatest blunder. It turns out he may have been wrong to abandon it. For 25 years after the 1998 discovery, every observation seemed to confirm that dark energy was exactly this: constant, stable, eternal. The universe's accelerating expansion was a permanent condition. That was the consensus. That was the bedrock. Then came DESI. The Dark Energy Spectroscopic Instrument is mounted on the Nicholas U. Mayle 4-meter telescope at Kitt Peak National Observatory in Arizona. It is not a conventional telescope in the way most people imagine one. It doesn't just take pictures of the sky. It simultaneously measures the light spectra of 5,000 galaxies at once, analyzing how that light has stretched during its journey across the expanding universe, and from that stretching, calculating how far away each galaxy is and how fast space itself is growing between us. DESI is an international experiment with more than 900 researchers from over 70 institutions around the world. It is, in every sense, a machine for reading the expansion history of the cosmos. On March 19, 2025, scientists announced the results of a new analysis using the first 3 years of data from DESI, involving some 15 million galaxies and quasars, covering 11 billion years of cosmic history. What they found did not quietly adjust a parameter somewhere in a model. It pulled at a thread that runs through the entire fabric of modern cosmology. When DESI's data was paired with other measurements, including the light left over from the dawn of the universe, exploding stars, and how light from distant galaxies is warped by gravity, there were mounting indications that the impact of dark energy may be weakening over time. Not constant, not eternal, Weakening. Scientists have believed dark energy was a cosmological constant, but it is actually changing over time in unexpected ways. Mustafa Ishaq, co-chair of DESI and an astrophysics professor at the University of Texas at Dallas, stated that current data shows that at the beginning of the universe, dark energy was very strong, but has weakened with time and will continue to do so. Let that sink in. The force that makes up 70% of everything, the invisible engine driving the universe's entire expansion, was stronger in the past and is getting weaker now. That single sentence collapses the story we've been telling ourselves for 25 years. And then it gets more extraordinary. Because if dark energy is weakening, the ending of the universe changes entirely. DESI's findings bolster the theory that the universe is going to end with a big crunch. While dark energy is weakening, matter is not. Weak dark energy could strengthen matter's influence, which eventually could be the force that causes the universe to collapse on itself. The Big Freeze, our cold, quiet, eternal fade into darkness, may not be the universe's fate after all. Instead of endless expansion, there is now a real possibility, not certain but no longer dismissible, that expansion slows, reverses, and everything in the universe, every galaxy, every star, every atom, comes crashing back together in a final catastrophic implosion. If that were to happen, it won't occur for at least another 20 billion years. The point is not the timeline. The point is that we thought we knew which direction this story was going, and now we don't. A separate study published in November 2025 in the monthly notices of the Royal Astronomical Society pushed the findings even further. A team led by Professor Young-Wook Lee at Yonsei University in South Korea reanalyzed supernova data using a correction for a subtle bias in how the age of the host galaxies was being handled. After applying the correction, the dataset no longer supported the standard cosmological model, but instead aligned far better with a time-varying dark energy model favored by DESI's own baryonic acoustic oscillation and cosmic microwave background data. Their analysis led to a conclusion that went further than even DESI's official findings. The universe has already entered a phase of decelerated expansion at the present epoch, and dark energy may have weakened to the point where the expansion has already started to slow. If that is true, we are not just predicting a different future. We are living in a different present than we thought. Now, scientists are appropriately cautious. DESI's findings are still shy of the 5 sigma threshold that physicists consider to be a firmer line for new discoveries, where a result will happen by accident only 1 in 3.5 million times. The current evidence is compelling, but not yet definitive. Other objections are harder to brush aside. If the DESI findings are correct, they might violate what's been labeled the null energy condition, which states that the energy density of a region of space cannot be negative. The exact interpretation of all these criticisms is still being debated within the community. This is not a settled discovery. It is a live, urgent, and deeply consequential scientific argument happening right now, in real time, between some of the sharpest minds in physics. But here is what makes this moment genuinely historic, regardless of how the debate resolves. We built an instrument sensitive enough to detect the evolution of dark energy across 11 billion years of cosmic history. We mapped 15 million galaxies, measured the ancient sound waves from the Big Bang frozen into the distribution of matter across the universe, and used them as a ruler to track how space itself has expanded epoch by epoch. And the answer that came back doesn't fit the model. That is not a failure. That is science working exactly as it should, reaching into the unknown and returning with something that demands we think harder, question deeper, and rebuild our understanding from stronger foundations. Further insights will likely come from the Vera C. Rubin Observatory, a ground-based all-sky survey in Chile, which will not only expand the supernova dataset, but provide a flood of new data on the evolution of large-scale structure over cosmic history. Its first images were released in 2025, and the data it will generate over the next decade could either confirm the DSI findings beyond any reasonable doubt, or reveal that we are chasing a ghost in the numbers. Either outcome reshapes cosmology. What is already certain is this: the force that governs the ultimate fate of the universe the single most dominant constituent of everything that exists, is not behaving the way we assumed. For 25 years, we looked at the sky and thought we understood what we were watching. A universe on a single, fixed trajectory, expanding forever, cooling forever, fading forever. We may have been watching it slow down the whole time and never noticed. The universe is not what we thought it was. And the most unsettling version of that sentence is that we are only just beginning to find out what it actually is. And that's it from this video. See you in the next one.